Okay, Biostats class, we're going to do an example of linear regression in Excel, and we're going to use a data set that's in your textbook. Dr. Beckman also used it in his PowerPoint, and basically it shows the relationship between iguana body size and egg number. Now ideally, when you do regression, you're using data from an experiment, and this isn't experimental data, this is observational data, or survey data sometimes called, but it's observation data. But here it seems likely that there would be a causal relationship between these two variables. Big iguanas, a big female iguana, has more room in its body cavity, it can probably eat more, process more energy, and make more eggs. And so we expect bigger females to make more eggs, and that could be causal, but you got to be a little careful here because it's observational. Perhaps there's another variable which drives both. Maybe big females can take over the best territories, get access to more resources, and therefore make more eggs. And so it's really territory quality that's driving egg size, and territory quality is a function of both how big the female is and how many eggs she has. But in any event, we're going to do linear regression on these data, and I'm going to show you how to do that quickly and easily in Excel. So the first thing you want to do is you want to graph your data. So let's look at this. We're going to insert a scatter plot. And we're going to delete the scatter plot I just made because I forgot to highlight my data. So here's the scatter plot. And if we want to get a trend line in here quickly and do a linear regression super quickly, we can just hover over a point and then do a right click. And when you do this right click, you'll get lots of options, but you can add a trend line. I'm going to add the trend line. It gives you options. We want to do a linear trend line, right? Not exponential or polynomial. These are different kinds of regression. We're doing straight line, linear regression. And we're going to display the regression equation on the chart and also display the R-squared value because we want to know basically how well the data fit that line. If R-squared was exactly 1, all those data points would fall on a straight line. There's some scatter here, and so R-squared is 0.906. About 91% of all the variation in number of eggs is associated with adult female body weight. And so there's a pretty good straight line relationship here. You can see that it doesn't look curved in any way. And so it seems reasonable to do linear regression analysis. And so we've done a fast linear regression analysis here. And I could ask you some questions. One of the things you need to be able to do is make predictions. So if you had a female with a 2 kilogram mass, right, mass is body weight, what is the predicted number of eggs? In order to get at that question, what you're going to do is you're going to take that equation right in there and operationalize it. So the slope here is 32.066. And remember, that has units. It's got units of rise over run, and so it's 32.066 eggs per kilogram of body weight. And then there's the y-intercept, which also has units in terms of eggs. But in any event, so if we put this into an equation, we're going to say equal 32.066 times the x we care about, which is 2 kilograms, plus and I get 65.5868 eggs, right? And so that's how many eggs this big 2-kilogram female iguana should produce. Now, one of the questions is, you can always do this, but sometimes it's a really bad idea to have any faith or in your estimate. So the way to figure out if you think you should have some confidence in your estimate is, first of all, do the data look linear? Yes. Is R squared high? Yes. Both of those mean this is a reasonable place to make a prediction. But a third thing that's really important is, are you extrapolating beyond the bounds of your data? And so our data run from right around 1 kilogram to about 1.7 or 1.8 kilograms. 2 kilograms, we're extrapolating beyond the bounds of our data. And maybe this line flattens out, maybe it curves upwards. We're assuming, without any data, that it continues in a nice linear fashion. And that's really dangerous. Sometimes data are very linear in one area, but for example, in this case, you get down here, it probably drops to 0, that female iguanas, say, that weigh this much, quite likely don't produce any eggs. And once if a female got too big, maybe it would take too much energy to maintain herself, and she would actually start producing not as many eggs. In any event, you shouldn't trust this prediction because you've extrapolated beyond the bounds of your data. Now, to get a full regression analysis here, what we want to do is go into data analysis, and you're going to pull up under R for regression this menu. And so the menu wants to know what your input range is, and so your input Y range is going to be number of eggs. That is our dependent variable. X, the independent variable, is body mass in kilograms. I included labels when I grabbed those data. And I'm just going to say, put this on a new worksheet page. And so when I click, I get this. I'm going to jack up my fonts to make it easier to see. I'm going to pull open these tabs a little bit. To get a better look at it. And so in Excel, when we do linear regression analysis, we get a lot of different things back. And so starting at the top of the page, we get our R squared and its square root, which it calls multiple R, that's Pearson's R, it's the correlation coefficient. So that's the correlation coefficient, that's R squared, right? We already knew that. I always look at the number of observations, because we had 11 iguanas in our data set, that number better equal 11. This is something you've seen before, it's an ANOVA table. This is a different utilization of analysis of variance. It tells us whether we have a statistically significant regression. And so here you can see it says regression. Don't worry about all these numbers. The numbers that really matter are the test statistic F, which is 8.67, and what really matters, the significance F, is the p-value. And you interpret this p-value the way you interpret other p-values. The null hypothesis here is that the regression has no predictive value, that there's no association between x and y in a linear sense. Because this is less than 0.05 by a lot, we reject the null hypothesis, and so this tells us we've got a statistically significant regression. Put in terms of your data, it means there's a statistically significant linear regression between the body mass of female iguanas and the number of eggs they lay. Down here, these two numbers are also interesting, and you've seen them before. I'm going to highlight them. It's kind of weird. These are coefficients, and it gives them weird names. Excel likes to give things weird names. The intercept coefficient is just the y-intercept. It doesn't give you units, but the units are eggs. The mass coefficient, well, mass is x. That's the slope. And so it doesn't say that's the slope, but this 32.066 is in units of eggs per kilogram of body weight, and that is the slope. I'm not going to go into all this, but basically you can interpret these and those, and you've got your linear regression done. Generally speaking, when you do a linear regression, you want to start by making a graph, just to make sure your data look linear. You know, if these data had big curvature, you wouldn't want to do linear regression because it's not linear data. And making a graph is a quick and easy way to kind of eyeball your data, get an equation, get an R-squared, and then if you want to know if that's a statistically significant regression, go into the data analysis thing, under R for regression, do regression, and get your ANOVA table here on sheet 2, and simply look at your p-value. Less than 0.05, statistically significant regression. Greater than 0.05, no statistically significant association between x and y in that linear sense. Okay, so there's a quick example of regression analysis in Excel. Try that, practice it. You can make up some numbers and try it. Think about what would happen if you had two random variables, right? If you had two random variables and you did a regression, would you expect a statistically significant association? Would your scatter plot look like a shotgun blast? Play around with it a little, get comfortable, and make sure you understand linear regression. Thank you.